Hi there, and welcome to the video for section 2.5 on the topic of matrix transformations, rotations, and dilations. So in this section, we're going to look certainly more at matrices. That's given away right away in the title here. But we're going to see how multiplication by matrices really affects the column vectors we might multiply on. And we're actually going to think of this through the idea of transformations of that vector that we're multiplying. But we do want to start just with this idea of a transformation. We'll see how matrices play into that idea later. So let's start here at the beginning. A function, which is really all we're talking about, is otherwise called a transformation here. And it's just a rule that assigns to each element of one set of vectors a unique element of another set of vectors. We care mostly about linear transformations, as it turns out. We'll get more into that. The reason it turns out we like linear transformations is because we'll see what this means in exact terms later, but it turns out they preserve the vector space structure in some important ways. We'll see exactly what we mean by that later, but for now, we just kind of want to remember that linear transformations, whatever that means, are the ones that we're looking for. We're going to figure out what it means later. So just to make sure we're on the same page here, a little quick, easy example. Given a function like f of x equals the cube root of x, we could say that the image of the number 8 under this function f is the number 2, right? In other words, f of 8 equals 2 in this case. This is the sort of language we'll use to describe functions, and the inputs and outputs. The image of an input under a function is whatever output you get there. We're going to use that same sort of language when we talk about transformations, because we said those really are just functions. But we want to extend these basic ideas like function f of x, a function of one variable. The way we talk about those, we want to extend that to vector spaces. Certainly we didn't think of vector spaces when we first saw functions like this in, say, an algebra class years ago. So let's look at an example to get into this a little more. If I look at the transformation t, defined by t of xy equaling this column vector, where the first entry of the column is 3x plus y, so 3 of the x values you have plus the y value, and the second component is 4 times the z value of your input here. All we're saying is that this takes elements from of the form x, y, z, so elements in R3, to elements that really only have 2 entries, right? 2 real numbers as their components. So that's taking it to R2. Now you're noticing here that I'm using a row as the input for this function t, this transformation t. I'm using a column for the output. As it turns out, we have some flexibility here. We'll play with that idea more. But for now, just know that it really doesn't matter how I write the input here, the x, y, z on the left side. I could write that as a column or a row, and we'll have the same meaning for this transformation. So let's establish some things. We say the domain of t in this case, right? That's where all the input values live. So that is R3 in this case. The x, y, z vectors that are being input to t are in R3. That's called the domain. The codomain, or you might think of this as the range, the values that come out, are in R2. So we call the codomain R2. Now we're going to be a little bit careful with how we describe range in codomain. We'll have very careful terminology for this word range later on. So probably it's best to stick with the word codomain here. Domain is inputs, codomain is outputs of transformation t. I should say domain is where the inputs live, R3. Codomain is where the outputs live, in R2. Okay, so just to make sure we see how the input-output functions work here, or input-output operations work here. If I want to look at this example, where I'm taking my transformation t defined above, but evaluating t of 4, -1, 2, well, this shouldn't be too difficult at all. It should be quite easy. All we have to do is follow these rules here, right? The first entry of this output is going to be 3 times the x value plus the y value. 3 times 4 plus -1. And the second component will just be 4 times the z value, so 4 times 2. And so we put this together, we see what we get. 12 plus -1 is 11. 4 times 2 is 8. And so the output that goes with 4, -1, 2 is 11, 8. You could have written this even with row vectors or row matrices. This would be just the same for our purposes here. For establishing what is that output in R2, well, we said elements in R2 could be expressed as columns or rows, so it really doesn't matter which we use. I use columns to begin with on the right side because we have that on the right side of the initial definition of T, but you can switch it to a row if you like. It might be a good rule of thumb to write the outputs in the same form the inputs are shown. So maybe if I do the input as a row, I would do the output as a row. We'll see we have a lot of flexibility here. And the next little part is showing exactly that. I could equivalently write this same thing I just did as T of this column 4, -1, 2 instead of the row 4, -1, 2. Then it would maybe be a little more appropriate to write the output, same 11, 8 output as a column as well. Okay, so that's the basic idea here, right? This works just like a function of multiple variables, except you might have multiple components to fill up, right? First one is 3x plus y. The second one is 4z. Okay. What we really want to talk about is, in this course especially, is transformations that can be described by matrix multiplication. And that's really going to get us to this bridge from transformations to matrices. So notice here, if I defined T of this column XYZ input to equal the matrix 310004 times that input, right? So I'm writing T, this is like our function evaluated at the input XYZ, is defined just to equal this fixed matrix 310004 multiplied on the column XYZ. If I define this matrix multiplication to be what T does to the input, multiplies it by that matrix, it turns out in this case, you can compute this multiplication and check out what you get. This is 2 by 3, 3 by 1, so we expect the result to be 2 by 1. But what do you get here, right? To fill up the first component of this output, you would take the first row of the matrix being multiplied to the left, and the first column of the matrix being multiplied to the right. Lay the column over the row, right? You're really doing a dot product with these two elements of R3. And what do you get? 3x, 3 times x, plus 1 times y, plus 0 times z. I won't even write that. And what about the next entry? That would be saying to take the next row, that's in the second row, with that first column, and do the same sort of dot product here. You'll notice you get 0 times x plus 0 times y plus 4 times z. So somehow this output that we had our T defined in terms of before, up here we just said T is this column of 2 entries here in terms of the x, y, z that you input. But here we saw we could write the exact same function as a matrix multiplication on the input column vector. And the result is that same exact output, 3x plus y, 4z. So this is what we mean by a transformation that can be described by matrix multiplication, right? T, as we described it up here, it turns out could be described by multiplying the input by a constant matrix. So notice, just as I was saying, we get the same transformation as above. And really, this idea that some transformations, not all of them, that's important, not all of them, but some transformations, like this one up here, can be expressed as matrix multiplication. In that case, we would say this matrix we're actually multiplying by, we'll write T of vector x equals ax. Right, this is my A, this is like my X. All we're saying here is that if a transformation applied to the input is really just matrix multiplication on the input, then in that case, we call this matrix A representative matrix for the transformation. everything about that transformation is tied up in that matrix. All the information about that transformation is tied up in that matrix A. That matrix represents the transformation. I want to reiterate, you cannot always do this. There are certainly transformations that cannot be expressed as matrix multiplication. We're just saying when it can be, then that matrix is said to represent the transformation T. Okay, and there are various other cases where you can do this, where you have a transformation that's expressible as matrix multiplication. And we want to explore a few of those. All right, those are going to be the transformations we're concerned with most in this class, the ones that really can be expressed as just simple matrix multiplication. You might be wondering, well, what sort of transformation wouldn't be able to be expressed as matrix multiplication? Right? This will look pretty complicated, and we saw we could write that as a matrix multiplication. So what might happen in a case where we can't do that? Well, think pretty hard about this, but maybe consider what happens if you have a variable squared or a square root. Play around with this a little bit and see what happens if you don't have that nice linearity in your variables x, y, and z in each of those entries of the output. Definitely play with that a little. I want you to explore that, but come to office hours if you can't find an example. If every example you write down is somehow expressible by a matrix, come to office hours. Maybe we can find one that is not expressible as a matrix multiplication. Okay, so let's look at some of these that can be expressed as matrix multiplication, some of these transformations. Let's start out by considering dilations and contractions. It's just a very specific type of transformation. We call them dilations and contractions. So the way to motivate what these things are is to consider a transformation that takes an input xy. Right? So this is just seeming like the inputs are in R2. I'm writing the inputs as a column. And all it does is multiplies that column vector by R for some scalar R. That is, in this case, we're going to say positive. Notice what this would really do. We know how to take a scalar multiple, R times a vector, right? It just goes to each component of the vector. So notice that this just multiplies both coordinates of every xy in R2 by R. In other words, right, this thing I claim can be written, this same transformation can be written as this, this matrix R0, 0R times the column of inputs xy. Can we see why that works? For one, I think one really easy way to see why it works, I'll write it up here, is you can always multiply by an identity of the appropriate size, and it doesn't affect anything, right? I just slipped an identity in here. It's like multiplying by 1. The 2 by 2 identity multiplied on xy does not change xy, so I can write that in there. But then I can really now take that scalar R and apply it to the identity. Multiplying the R into the identity matrix tells us that same transformation, just taking a scalar multiple, a positive scalar multiple of xy, can be written as multiplying xy by the matrix R0, 0R. Right, so in this case, we would say this dilation and contraction transformation is really just defined by the matrix R0, 0R, because that's the matrix that the transformation looks the exact same as multiplication by. Multiplying by this guy is the same as applying T. Now let's parse out the details here. Dilation versus contraction. What's the difference? Why do we use two words here? Well, we say T is a dilation if that R value in this matrix is bigger than 1, right? In other words, all the distances from points in the domain to the origin in that same domain get increased by a factor of R when we map to the codomain, right? When we take the input and send it through the transformation and see what output we have. The output has all the distances from the origin multiplied. In the case that R is greater than 1, that means increased by a factor of R. So let's see this. Let's make sure we see this very clearly with this example down near the bottom of my page here. Let's do this example, T of 2, 1, where I'm going to take R equals 4 in this contraction dilation transformation. right? Certainly 4 is bigger than 1. So this is indeed a dilation by this definition. So let's see what this does. It says, just looking at this matrix with R equals 4 plugged in and multiplying on 2, 1. So we should see right away what this does. Row with column gives me 8 plus 0. Row with column gives me 4 times 1 plus 0. So the input was 2, 1. The output was 8, 4. So let's see visually what just happened here. If the input was 2, 1, I've marked that vector from the origin to the point 2, 1 in R2 in the plane. That's this little vector here, marked with 2, 1 as its coordinates. All we're saying is that if we instead take t of 2, 1, the effect of this transformation on that same input, this just stretches it out by a factor of 4, right? It's 1, 2, 3, 4 times as long, but in that same direction. This should just stretch out to the point, hopefully I did this somewhat accurately, 8, 4. But that is the image of this original vector, 2, 1, under the transformation t. So maybe now we see why this is called a dilation. All we did was dilated the length, right? We made the vector 2, 1, looks just the same direction, except it is lengthened by a factor of 4. To be clear, just the red vector is my output. These dotted lines are just for clarity. Okay, so that's a dilation transformation. Let's also see a contraction. Maybe I'll do the same thing as I did above, except now with an R value between 0 and 1. So not greater than 1, but between 0 and 1, like a half, for example. Well, we call that a contraction if the R value is between 0 and 1, because when we multiply all those distances by R, now we're multiplying by a number less than 1. So it's actually going to shrink all the distances from the origin. Right, so let's see what this vector 2, 4 looks like when we transform it with an R value of 2 under a contraction. Let's see what we get. We get just that same matrix, R0, 0, R, but with R equals 1/2 plugged in. But now our input's a little different. It's 2, 4 now. And you can do this matrix multiplication, or you can just think about what we're doing. We're contracting 2, 4 by a factor of 1/2. So what do we get? 1, 2. We just cut both entries in half. So in this case, we had our original vector drawn here. Again, that's stretching out to the original coordinates 2, 4, I'm saying. So each of these tick marks is 2. And then we apply the transformation. Let's do this one in blue. We apply the transformation to get 1, 2. But what does 1, 2 look like? It's just the exact same direction, but half the length to get to the point 1, 2. So that's the image of 2, 4 under transformation t. 2, 4. Right. So hopefully we see why we call it a contraction. When that R value is less than 1, still positive, but less than 1, right? What is it doing? It is now shrinking the length of the vector by a factor of R. Okay, so those are dilations and contractions. Now we want to talk about more of these transformations, certainly. Let's talk about reflections now. Things to keep in mind here is the whole reason we're going through this specific set of transformations, the contractions and dilations, reflections now, and other things we'll see, is because these are transformations that happen to be expressible as a matrix multiplication. Every one of these transformations we're talking about now has a matrix that defines it. So let's talk about reflections. Consider the transformation t applied to the input x, y in R2 equals x negative y in R2. Notice all we're saying here is that t maps inputs x, y in the domain to a point, or you can think of it as a vector, x negative y, that just has the y coordinate with an opposite sign compared to what it started with. You start with positive y, it flips that to a negative of whatever you started with. So all we're saying is that you started out with an xy pair, you ended up with x, but negative that same y. Think about what that really does. We'll see that in an example, so I wouldn't even draw it yet. All that's going to do is reflect the point across the x-axis, or reflect the vector across the x-axis. Maybe I will draw it. Right. If I have a point xy, meaning this is x on this axis and y on this axis, then that's my input. The output would be x negative y. That same x in this direction, but now negative as far as we went in the other direction. This is xy as a column. So this transformation described here, all it does is reflect the vector or the point you initially had to the opposite side of the x-axis. This is a reflection across the x-axis. And notice it's easy to write down. All we're doing is trying to introduce a negative on the y value. So you introduce a negative on the kind of the y column of the identity matrix to do that. But we saw that's just a little, all this is an elementary operation on the identity, where you just scaled the second row of the identity by -1. We know that has the same effect doing that to a column matrix, xy. Doing that same row operation, multiplying the second one by a negative, is equivalent to multiplying from the left by the identity with that same operation applied to it. We saw that when we discussed elementary matrices in a previous video. So it's easy to write down this matrix form of this transformation. If you didn't see that, maybe you just check that this works, right? Multiply this out. And you do see that it works. This row, this column gives me x. This row, this column gives me -y. So even if you don't remember or aren't using that quick fact about elementary matrices to get this guy, it should be pretty clear that it does work. Pretty easy to show that this does cause this same output. Okay, so this t, this reflection across the x-axis, that transformation is defined by 1, 0, 0, -1 by that matrix. Let's see an actual example using that. Let's take, for that reflection matrix across the x-axis, let's take t of 2, -1. T of 2, -1, I don't even need to really write it, but I will just to be clear, is just this matrix that defines t times the input, 2, -1. And all that is 2, +1. You can check me on that. You can easily just jump right to what the output is because you know the ultimate effect is just to flip the sign on the y value. And so we look at a little example here. I'll use yet another color, maybe green. My original input, the 2, -1 vector is drawn here. Let me draw the output. Instead of 2, -1, that's 2, +1. This is t of 2, -1. So we see that, yeah, it doesn't visually look like all we did was reflected this vector drawn in black across the x-axis to get the image. So that's all t really does. It takes all the points in the plane and flips them to the other side of the x-axis. Now you might ask, what about a reflection across the y-axis? Well, if this guy gives you a reflection across the x, maybe you can figure out how to do a reflection across the y-axis. I will leave that to you. I don't think it's too challenging. Be sure to stop by office hours if you can't figure that one out. We can chat about it, certainly. Maybe it's too obvious, I don't know. But it's one I want you to try to work out for yourself. Try to work out that matrix that defines a reflection across the y-axis. That'd be an interesting exercise. Now let's talk about another one of these transformations that can be represented by matrices. Another one is a rotation. We've seen contraction dilation, we've seen reflection. Now we're going to see a rotation transformation, can also be written as matrix multiplication. So let's consider the transformation T taking a point A, which I'm saying has coordinates x, y. I don't really like the notation I've used here, A, x, y like that. This looks a little too much like matrix multiplication. So I'm saying A is the point with coordinates x, y. I'm not saying we're doing matrix multiplication, A times x, y. A is a point with coordinates x, y. So consider the transformation that takes a point like that, x, y, I'm labeling that point A, and rotates it about the origin counterclockwise by an angle theta to some image, some place you end up after that rotation that I'll call point B with coordinates x prime, y prime. The primes there are just labels. They're not indicating a derivative or anything like that. They're just saying they're different than the original inputs. These are the output x and y values. That's fairly common with transformations to put these little prime, these little tick marks on the output coordinates to specify that those are what came out of the function. The ones without the tick marks went into the function. So we're saying x prime, y prime here is the output image. X, y itself is the input, and these two should be related. These points A and B should be related by really just an angle of theta, right? From A, rotate counterclockwise around the origin by an angle theta, and that's what we define. Where you land is the point we define to be B. So if we wanted a transformation T that does this, let's see how this works. So we're saying we're starting out in my picture here. We have some vector from the origin out to point A. That vector's components would be x, y, so that's like what we're starting with. And we're saying we want to apply some transformation to this input that's going to just rotate it around the origin, not changing the length from the origin, just rotating the angle about the origin by an amount theta in the counterclockwise direction. So wherever we started, let's call the angle from the positive axis, let's call that alpha. So this original angle that this point sat at was alpha above the x-axis, and we wanted to rotate theta more from there. And let's call that original distance that xy has from the origin, let's call that r. Notice that'll be the same as the distance of the image under our transformation, since we're just rotating, we're not changing distance from the origin. So what I want to do here is first recognize that with this setup, we could write our original inputs, x, y, as r cosine alpha, r sine alpha. Right, that's just by doing a little bit of trig. On this triangle. A little bit of trigonometry on there will tell you that your x coordinates really r times cosine of that angle, your y coordinates r times sine of that angle. Those should be fairly familiar from polar coordinates if you remember those. And so what's going to happen? Well, we rotate, get to this new point, and now the angle that this one sits at from the positive x-axis is now, let's look at this, alpha plus theta, right? The angle to here plus the angle that we went further. So we could write this x prime and y prime, the coordinates of the image, very similar to what we did down here, except we'll use the new angle, alpha plus theta. And then so over here, I've broken down what we get for each of those, right? X prime is just r cosine alpha plus theta. And all I did here to the next line is I applied an angle addition formula, an angle addition identity for cosine. And you can look that up and check it. You do get this result that we have. But notice what we really have sitting here. R cosine alpha, that's just the original x value we started with. And now it's being multiplied by cosine theta. minus r sine alpha, that's our original y value. Now that's being multiplied by sine theta. Similar for the y prime, we can look at things the same way, right? Y prime over here was r sine of alpha plus theta. So we start there and we apply an angle addition identity for sine. We get this result. You can check that. It works out pretty nice. But again, we see r sine alpha and r cosine alpha, which are the original xy coordinates. This was y. This was x. There we have it. So we've really kind of cracked the code here, right? We have figured out that this should output x cosine theta. Let me even write it like this. Cosine theta times x, give myself more space here, minus sine theta times y. That's the first entry. That's this guy. And the next one will be, I'm going to keep the x's coming first. So I'll put sine theta times x plus cosine theta times y. Right? And so how can we break this up into a matrix times the vector input x, y? That's what we're typically trying to do here. So let's see. Well, let's see if we can maybe unpack this with our minds here. Remember, we want to view the first entry here as being, we want to write this as a matrix times that input. Well, that first entry of the result should be the first row of this matrix multiplied on, really dotted with, this column xy. So what should this row be? It looks like we needed cosine theta and then negative sine theta. Likewise here, it looks like we need sine theta and cosine theta. And that makes this matrix multiplication work. You can write this out nicely over here. I guess I left myself room even though I did all the work in the corner over there. We have figured out what the outputs must look like, just copying that here. But over here, I claim we have found that the matrix that you'd have to multiply xy by to get this same result is really cosine theta, negative sine theta, sine theta, cosine theta. So this is pretty powerful. We've seen that whatever angle theta we want to rotate this pointer by around the origin, we should just multiply the input xy we started with by this matrix, cosine of that angle theta, negative sine of that angle theta, sine theta, cosine theta. It's a pretty easy little matrix to fill out if we know the angle theta that we want to rotate by. So in other words, we could say T, this rotation counterclockwise about the origin by an angle theta, that transformation is defined by this matrix that we could equivalently just multiply the input by. So there's our rotation matrix. You'll hear this called a rotation matrix. To make sure we see exactly how useful this is or how easy it is to use, let's look at an example. Oops, got a little typo here. Example to perform a rotation of pi/6 about the origin counterclockwise. So all we need to do is plug in theta equals pi/6 into this matrix that defines the rotation. Cosine of pi/6, do this math with me if you will, √3/2. Negative sine of pi/6 is -1/2. Sine of pi/6 is 1/2. Cosine is √3/2. So this matrix multiplication, multiplying your input by this specific matrix, is a specific rotation of pi/6 counterclockwise around the origin. In other words, rotation by pi/6 is defined by this matrix. That's a transformation defined by this matrix. Okay. So we've seen quite a few of these. I do want to note here, we've only named square matrix transformations, right? Matrix transformations that can be expressed as multiplication by a square matrix. That's important, the square part. But recall that first example we saw actually shows that we can have a transformation not defined by a square matrix, right? We saw that already. Let's go back up there. This guy, that transformation we started with, that didn't have a square matrix. How was that different than the ones we've seen since then? Well, all the other ones were taking elements of R2 back to R2. Notice this matrix not being square really meant that we took elements in R3 and returned them to elements in R2. Right, so we've changed the, in this case, the domain and codomain have a different dimension. And that's what happens in general when you have a non-square matrix defining your transformation. So let's summarize exactly what I was describing, right? In that case, the codomain and domain have unequal dimension. So to go from Rn to Rm with a matrix transformation, we need a transformation T that takes elements in Rn, right? That's where we're starting, and applies matrix multiplication by some matrix A on that input, that column of entries x1 through xn. But that matrix, in order to return objects in Rm, that matrix A must have m rows and n columns, so not a square. Really study this. Make sure you really see what we're saying here. Why that matrix has to have m by n dimensions for the transformation it defines to take elements from Rn to Rm. Really study that. It's a key idea here. Okay. So let's talk now more generally about matrix transformations. We've seen that we named some of these, specifically ones that had a square matrix that define these transformations, right? That's the contractions and dilations, that's reflections, that is rotations. But we've seen at least one example where we didn't even have square matrices. So we want to talk in general about matrix transformations. All of these under one umbrella have some nice characteristics we want to describe. What is it about a transformation that can be written as a matrix multiplication that makes it special? Well, here's some facts here. In fact, matrix transformations map line segments in the domain to other line segments in the codomain. If I take a segment of points, everything from here to here in the domain, and I map each one of those over to the codomain, the images there will form another segment, potentially of a different length, some in a different position, but it will map line segments to line segments. Also, if that matrix that defines your transformation is invertible, it's actually going to map parallel segments to parallel segments. A segment from here to here or from here to here, parallel segments, will both be mapped over to two new segments that are parallel in the codomain. Really nice property. And just the fact that matrix transformations map line segments to line segments gives us a really easy way to see how a polygon maps under some transformation defined by a matrix. All you do is map the vertices and then connect the dots in the codomain. So let's see an example of that. Let's show the image of triangle OPQ under the transformation T taking R2 to R2 defined by this matrix, 1, 2, 3, 1. Well, all we're going to do is look at our triangle OPQ that I've written here. O is the origin, P is the point 1, 2 in the domain, Q is the point 2, 1 in the domain. So we've got this little triangle with those points, OPQ, as the vertices. Now, what we set up here is all I'm going to do, what we set up here, is all I'm going to do to see the image of this triangle, of every point on this triangle under T. I don't have to plot, and I don't have to run every point that sits on this boundary through the transformation. Just run the vertices through the transformation. Those will each plot to some new points in the codomain, and then we connect the dots, and that will be the transformation of this entire set of points on the triangle. So this is easy. T0, 0, we're saying T is defined by multiplication by that matrix A, so we're just multiplying the input by A. what do we get? We get the 0 vector. So right away, let me do this in red maybe. The point at the origin mapped to the point at the origin. So this is t of 0, 0 in red. This was 0, 0 in the domain where it came from. Well, if I do the next vertex, if I plot, or if I plug in 1, 2 into my transformation, again, we're just multiplying 1, 2, the column 1, 2, by this matrix. What does that give me? If I multiply this out, it looks like I get 5 and 5. Let's plot this one. I'll do this one in blue. It started out at this point, 1, 2, and it moved to 5, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Somewhere right about out here. So that is t of 1, 2. Right? So the blue point up here, P, maps to this new point 5, 5 in the codomain. Now last one here, let's plug in the last one. 1, 2, 3, 1 multiplied on 2, 1. That's our Q point, that's our Q vertex. What does this give me? It looks like 4, 6, 7. So it looks like this one is roughly, I don't know, roughly about here. Oops, use another color here. There we go. This vertex maps here. And so we can see how our triangle changed, right? These vertices look like they kind of switch places somewhat, but the triangle is still just what we get. The image of the triangle OPQ is what we get by connecting all these dots. Oops. Now just use your imagination and act like that's a straight line for me. There we go. Right, so every little point on this segment maps to some point on this segment. Every little point on this segment maps to some point on this segment. And every little point on this segment maps to some point on this piece. In that sense, we say that triangle OPQ has this image that I've outlined in black in the codomain under transformation T. Okay, so this is what we meant by how to map a polygon under a transformation. Let's go a little bit further. Compositions, we can certainly apply more than one of these transformations to a given output, right? We could contract or dilate, then rotate, then maybe reflect. We can do a lot of these transformations all in sequence. And if we want to do that, if we want to apply in order transformations T1 and then T2 and then T3, all the way out to some nth transformation Tn, if we want to apply those transformations in that order, T1, then T2, all the way out to Tn being applied last, and we have a matrix that defines each of those. The matrix defining T1, if that's A1, and if the matrix defining T2 is called A2, and so on, then applying these transformations successively, one after another, is the same as just multiplying by these matrices one after another. Right? It makes easy sense. So if I want to apply T1 first, then T2 to my input, all the way out to Tn being applied last, that would be written this way. These little circles mean composition, one transformation applied after the other. All we have to do is apply the matrix multiplications that define those transformations in the same order. A1 times x, A2 times that result, A3 times that whole result, and so on until you've multiplied by your last AN matrix representing Tn. Okay, let's see what else we can do. Well, I suppose it's useful to define orthogonal transformations. These are a very important type. It turns out one way we can define an orthogonal transformation is to say that an invertible matrix A, first of all, we'll get to the idea of an orthogonal transformation. We start with a definition here. An invertible matrix A is called orthogonal. It's an orthogonal matrix if its inverse is really just its transpose. We're going to talk about that idea more later, but think about what it would mean that A transpose times A is really the inverse times A, which means you get the identity, right? For an orthogonal matrix A transpose A is the identity, and A transpose must be the identity. Think about what that means. What has to be going on with this matrix A to make it orthogonal? It turns out, though, that if you have this property that interchanging rows and columns actually produces the inverse, that's a pretty strange property to wrap our minds around. But if you have a matrix with that property, an orthogonal matrix, then an orthogonal transformation is just a transformation defined by an orthogonal matrix, right? And a transformation T such that applying T is equivalent to multiplying by your orthogonal matrix A. Some facts about these things, why we care about orthogonal transformations. We'll talk about why these orthogonal matrices are useful a little bit more later in the course. But for now, just speaking about orthogonal transformations, what are some useful properties of these things? Well, orthogonal transformations, we say they preserve norms, angles, and distances, meaning that the norm, the length of a vector u, is the same length as its image under this orthogonal transformation, right? The vector that gets output from this transformation is the same length as the vector you started with. The transformation preserved its norm, its length. Another way of stating what it means that that orthogonal transformations preserve angles as well is written here, item 2. The angle between u and v is equal to the angle between t of u and t of v. Right? So the angle between two domain vectors is going to be the same as the angle between their images in the codomain. That's a huge idea here. Also, going along with this is the fact that orthogonal transformations preserve distances. And another way of stating that is the distance between u and v, so the norm of their difference, that's the distance between them, is equal to the distance between their images. If you start out with 2 points this far away in the domain, when you map them to the codomain under an orthogonal transformation, they stay that same distance away from each other. Things might be changed around this way or flipped around somehow, but that distance between your points remains intact, remains unchanged. And so maybe you're already thinking about this, thinking, well, it preserves norms, so all my lengths stay the same. It preserves angles between two vectors. So if I move them, those vectors kind of stay together, it looks like. And it preserves distances. So if I start out with two things here, when I move them over, they're the same distance apart. Have we seen any transformations so far that seem like they might fit this description? Think about that pretty critically. Think if you can identify any of the transformations we've done so far that might be considered orthogonal transformations. Think hard about that. And I claim, I'll give you a little hint, think about rotations and reflections. That's going to be my hint to you. I think those are good candidates to try to test out. Is a rotation somehow going to be, is a rotation matrix orthogonal? Is a, where is it? Is a reflection matrix orthogonal? You can test these out and you can find out that answer for yourself, or maybe come to office hours and talk more about it. But I think that's a good place to start looking to get a sense of what these orthogonal transformations, how you might think about them. Think about rotations and reflections. See if you think those are orthogonal transformations. Okay, now finally, let's get down to it. Not all transformations can be written as a matrix multiplication. In other words, not all transformations are matrix transformations, right? So a few examples of these is a translation. If we just slide a point in the domain somewhere else in the codomain, we translate it, we move it from one spot to another. We could do this to, if we had a transformation that does that to one point, we could do that to a whole set of points, like to a triangle. Maybe we have a triangle somewhere in the domain. A translation will just move that triangle to a new place in the codomain. So let's define that. We say a translation transformation is defined to be some transformation T that takes the input U and just adds a fixed vector V to it, right? So a constant vector. This isn't, we're thinking of this as being a fixed value. U is kind of like your variable vector, your input. You have control over choosing that in Rn. This V is prescribed. It's part of the transformation. It's like a function f of x equals x plus 1. The x is an input there. The 1 is a fixed value. So this translation here, u plus v, maps all the points defined by u in the domain to an image shifted a distance and direction defined by vector v. So if vector v has a certain length to it, you're going to shift that far. If you know the direction v points in, you're also going to shift in that direction that far. Let's see how this works again by considering the image of a triangle, OAB, where A is the point 1, 3, B is the point 1, 1, and O again is the origin. Don't be thrown off by my notation here. This isn't a matrix A or a matrix B. These are just points being labeled as A and B. Let's consider the image of this little triangle under this transformation, x, y plus 3, 2. Maybe you can guess. Let's draw this. What's going to happen? We originally had this triangle with points at 0, 0, 1, 1, and 1, 3, which I've roughly drawn this way. And so now what we're going to do is shift that by this vector 3, 2. All these vertices, just translate them by a vector 3, 2. Let me do this one at a time. If I take the origin and translate it by the vector 3, 2, I'm moving to the point 3, 2. 1, 2, 3. It's about there. So that point moved there. Let me even erase that arrow. I don't want that arrow. Okay. Okay. Now let's translate this point that was at 1, 1. Well, if I take 1, 1 and I add 3, 2, you can see where I go. All I'm really doing is translating by that same vector 3, 2. So I go 3 more in the x, 2 more in the y. It looks like I end up somewhere out here. That would be the point 4, 3. Yeah, it looks roughly believable. But that's t of 1, 1. And finally, my last vertex here, that was the point 1, 3. If I plug in 1, 3 here and add 3, 2, I get 4, 5. So 4, 5 would be, I don't know, roughly 4, 2 higher, roughly here. So notice, I hope we notice that our shape didn't change at all. All it did was moved to here. That's all that happened here, right? So this entire shape, when we get yet another color, strange color here, all that happened there, it's a galactic arrow there. I think there's stars and galaxies behind that in that ink. That's kind of a weird pen to use, sorry. This vector here is that constant translation 3, 2. So we've just taken this whole shape and translated by this vector 3, 2. We've just moved it in space, right? So that's what a translation does. But notice you cannot write this as a single matrix times x, y. There's no way to account for adding 3, 2 to that result Just the xy alone, you could just multiply that by the identity. But to add a 3, 2 at the end will require something more than just matrix transformations. So a translation is not a matrix transformation. It turns out another transformation that is not a matrix transformation is called an affine transformation. An affine transformation T, taking Rn back to Rn, so one space to the same space again, defined by T of U equals a matrix transformation, A times U, plus a translation, V. Right, so that's all we mean by an affine transformation. If you see that word, it just means it's a matrix transformation, but then with a translation tacked onto the end. So you might think about the ability you have to transform these objects if you could do any transformation, any matrix transformation you want, but then also slide it anywhere in the plane with a translation. There's many things you can do with an affine transformation, but yet again, there's no way to account for adding a fixed vector just by doing matrix multiplication. So this is not a matrix transformation. It's a matrix transformation followed by a translation, which cannot be written overall as a single multiplication by a matrix. All right, so these are some pretty simple examples of non-matrix transformations. There are many more, but here's a couple examples for you to play with. These ones are maybe still useful, but not matrix transformations. Okay, that is it for this section. More in the next video. Thank you for your attention. I hope this was useful.